So what is recursion? Well, recursion is when something is defined in terms of itself. The matryoshka is there because I think that's a very good example of recursion, because each matryoshka contains one matryoshka. So basically, a matryoshka is defined in terms of itself, right? The factorial function can also be defined in terms of itself. Because when we do, for example, factorial of 5, we're basically decomposing it until we get into an indivisible unit, which is the factorial of 1. And then we start multiplicating back because we got to the indivisible unit. And basically, the factorial of 5 is equal to 5 times the factorial of 4. And as you can see, the very definition of factorial needs its own definition, right? So this is what happens when you have, for example, a factorial function and you call it with 5. So first thing, you're gonna do 5 times the factorial of 5 minus 1, and you keep doing that until you get to the indivisible unit, which is the factorial of 1. And by definition, the factorial of 1 is our indivisible unit. It's 1. So basically, we get that result. We don't bow anymore. And then we get 120 back because we multiply all the results, right? Easy, simple. And well, I thought this song wouldn't play because I had problems with this last time. So I can just write a simple factorial function, which we'll use in the later examples. I'll do some live coding, which is very dangerous. Let's see how it goes. Cool. So I'll do factorial live.js. Do I have that? OK, cool. So basically, what is a factorial function? A factorial function, it takes a number, right? And if that number is 0, we will return 1. Otherwise, we just call factorial itself with n minus 1. And we will multiply that by, not 5, n, right? So now, if we call it with 5, we'll see what happens. I'm console logging the result here. Cool. No ESLint rules. Cool. Factorial live. Cool. So that's 120. So what's happening here? Basically, in the first time this function is called, n becomes 5, and then I call factorial, which is this function itself, with 4, because that's 5 minus 1, obviously, until it gets to 0, and then I get 1 back. By the time I get 1 back, I've gotten like 5 times 4 times 3 times 2 times 1, and then I just multiply that and I get back the result. Cool. So basically, this is what happens when you call the factorial function. And this is like a very basic example, but we'll get into more complicated things later, I promise you. So basically, we keep decomposing calls until we get to the bottom of them, and then we do the multiplication and get back 120, because the factorial of 1, which is this, returns 1. OK, so let's talk about how to visualize recursion. So I've just done this. Well, in the Fibonacci function, for example, so when you do the Fibonacci of 4, what's happening is you're gonna get when you try to get the fourth number in the Fibonacci. Actually, it's the 5th number because this is the index. But anyway, when you try to get the 5th number in the Fibonacci sequence, you're trying to get the previous 2 numbers and get the sum of them, right? So basically, can you still hear me? I hope so. So basically, when you do Fibonacci of 4, you'll be doing Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? So basically, each call to Fibonacci is going to decompose in 2 other calls until we get to the bottom, to the divisible units, which is Fibonacci of 1, which is 1, and Fibonacci 0, which is also 1, right? Because those are the first numbers in the Fibonacci sequence. So once I get here, I have numbers, and I can just sum them, and then I can bubble all the way back to the root of the tree with those calls, right? And I can even write this. So let's just use this very same file. So I can define Fibonacci this way. So Fibonacci takes a number. And if this number is lesser or equal to 1, we will just return 1. Otherwise, we will do Fibonacci of n minus 1 plus Fibonacci of n minus 2. Is this font size all right for you?
Yes.
Cool. So I can just do this. Let's use a bunch of numbers here. Cool. There you go, Fibonacci. So how do you actually think recursively? Well, I'd say that the first thing you have to do is to break down the problem. So you find what is the indivisible unit, because that's when you exit, right? That's when your recursion will stop. You identify the base cases, right? And then you also abstract the calls, because if you keep thinking about what happens once you call the recursive function, your mind will get too deep into it and it's going to become hard. You just got to trust that you have identified the base cases correctly, the indivisible cases, and then you got to trust that you're gonna break down the problem in the right way for it to return those base cases, to exit the recursion, right? That's how I like to think about it. I think that's the best way to think about recursion. So in order to show you how I do this, I'm gonna do a simple algorithm to check if a number is present or not in a binary search tree. Cool, so I've got a file here with a tree structure. Cool, it's here. So basically, as you can see in this slide, every one of these nodes is kind of like a tree, right? So this is the root of this tree, and it has a children in the left and the children in the right, right? And each one of these can be thought as the same unit. So they're just like smaller units of the same problem, because for each one of these nodes right here, I'm gonna just check the children in the left and the right, okay, until I get to an indivisible unit. Cool. So let's implement find. So find takes a node, right, and a number. So I can just do this. So what's the first case? The first case is if node dot value, I don't quite remember the structure of this. Yep, value is equal to n, I can just return true. Otherwise, I'll just check if n is bigger than node.value. And if that's the case, I'll do find of node. So if it's bigger, I should go to the right, because the nodes in the right are bigger than the value in the root, okay? So I can just do find node dot right, and then I can just pass n there. Please correct me if I do anything wrong, if I miss any parentheses or anything. Otherwise, I'll go to the left, right? So I'll do find left. And another case that might happen is if I reach a node which is undefined, right? Because I can get to an undefined node, and that's also one of the cases I gotta think about. So if node is undefined, I just return false, right? So that's my find function. No ESLint rules. Now I can just call find with, let's see what number it is here, 4, and see if it works. Otherwise I might have to fix it. And you're gonna help me. Cool. Oh, I didn't log it, but I didn't got any Stack Overflows. That's a good sign. Cool. Whoa, first time. Cool. I swear I haven't practiced this at home, so very, very happy right now. What's one number we don't have here? 5. So this returns false. Oh, I've done something wrong, right? Is 5 here? No, it's not. Okay, now it's the hard part, right? So anyone has got any ideas?
Not passing the tree on the console log find.
Oh, that's true. That's true. That's completely true. So I gotta pass the tree. Very obvious mistake. Cool, so that's good. That's better. Look, and now it works for real. I'm not just lying to you. What's your name, mate?
Steven.
Okay, so thanks to Steven, we got it working. Thank you, Steven. And well, in recursion, there are plenty of ideas to explore. So if you feel like solving hardest problems, just like Google for any of these. Or if you just feel like learning Lisp, I think that's going to be really awesome for you. But now let's take a look at what happens when you do recursion. Right, so I present you the stack. This is the thing that blows up in your face when you do things wrong, right? So every time you do a function call, you stack a new item in the stack. So the stack is last in, first out data structure. So the last item to come in is the first item to come out. So every time you do a function call, you get a new frame on the stack with the data for that function call. And if you do any subsequent function calls inside that function call, that goes on top of the last frame. So you just keep like stacking things up so that you can like know where you are. So I've got an example here that makes things really easy to understand. So here we're doing half of what's inside here. So this is the bottom of the stack. We have nothing there. So the first thing we get is to the inside of half, right? So we got to call to half. Then we've got double, because that's inside of double. Because we're calculating the first thing, the first term there. And then we got to run mathpal, right, with 2 and 3. So once that returns the result, we can actually calculate double. And then once double is calculated, we get back to half. And now we find triple. So we stack another call to triple. And then once we get back the value of triple, we have both values inside the half expression. So we can just calculate half and get to the bottom of the stack, right? That's how the stack works. So in Fibonacci, basically, what you're doing here is you're stacking those calls until you get to the leaf nodes. And then you're like popping those frames out of the stack when they result like the result for the indivisible unit, which is like the first 2 numbers in the Fibonacci sequence. So basically, all the way until the Fibonacci of 1 and 0, you're just stacking calls there, right? Cool songs again. So I already implemented Fibonacci, so I don't have to do this again, but I'll do something else. I'll go back to Factorial Live. So just comment this out. Don't need this. Cool. And this becomes Factorial again. So I'm gonna make this return the same thing as it was returning before, but every time I call Factorial, I'm gonna do console.trace so that you can see the frames being stacked. Okay, cool. Node, oops, Factorial Live. There you go. So I actually have to decrease the font a bit. Let's see if this, oh, I split the screen, sorry. Okay, I hope you can kind of see it like this. Can you? Okay, so, oh, Chimox. Okay, so the first time, yes. So the first time you call Factorial, as you can see, we called Factorial Live here, and then we got to Factorial Live on line 2, because that's our console trace where it's printing. So the first thing we've got on our stack is this Factorial. It's on the top of the stack, right? So when it gets here, it needs to call Factorial with 4 again. So we need to stack that call. So here, we're stacking it again. So as you can see, we got Factorial Live twice in the stack. And the third time we call it again, adding another frame to the stack. And we do the same thing until we get to the indivisible unit, which is here. So we've got all these frames with data regarding factorial calculation in our stack, right? So this is the stack. And now let's talk about tail calls. So what are tail calls? Tail calls are functions that can be executed without growing the stack. So as you could see in the previous example, we were growing the stack on every call to Factorial, right? So with tail calls, there are always the last thing to be done and evaluated before return. we can not grow the stack. So the return value of this called function should be returned by the caller, and they should be the last thing to be evaluated, right? So this is the formal definition of it, if you feel like reading it. Oh, Firefox is installing updates, how lovely. Okay, I guess you'll be able to see it by yourself when I upload the slides later. Sorry, it's Firefox's fault. Okay, so after talking about proper tail calls, I'll show you what a tail call is. So basically, without tail calls, each frame depends on the frame above it. So when we calculate the factorial of 3, for example, we have to multiply 3 and the factorial of 3 minus 1, right? So when we get inside the factorial of 2, we still have to have this 3 here. Because once we pop that frame out of the stack, we want to get the result of factorial 2 to calculate, right? So we're going to stack frames until we get to the indivisible unit. And then once we get that result, we can start popping those frames out because we don't need the data in them anymore, right? So once we get to the indivisible unit, we have all the data we need in that top frame. So you can just pop frames out until we get to the bottom of stacks, right? So then we unwind. So with proper tail calls, what we're able to do is we're able to pass an accumulator to every function. So every function has all the data it needs to execute. So we don't need to stack frames anymore. Because on every call to factorial, I won't need data from previous frames. So as you can see, I can just increase the accumulator, and passing the next number you should calculate the factorial for until I get the result, right? So proper tail calls uses less memory because I do local allocation and I can have better garbage collection because all the data I need is self-contained in a single frame. Like all the variables that have been used in other calls, I don't need them anymore. And I also need less memory for the stack because I'm not growing it. Well, this is not a huge performance update, but it's worth noticing. More songs. So, where is it? So let's do that. Can do that here. Okay. So now, cheers. So I can just, as I said, I can pass in the accumulator, which is this. So I can just do n here, which is the accumulator, n times ACC, sorry. So I'm going to do n times the value I have accumulated. And I think that's basically all I got to do. Oh, how brilliant. Okay. Cool. That's now I got to do. Node n times ACC. So for every call of factorial, oops, sorry. So I'm passing the accumulator here.
Shouldn't you initialize it?
Oh yeah, that's true. Sorry. Default param, but that's not it. Oh. Nope. So I'm doing n equals 0, I return 1. Otherwise, I'm going to calculate the factorial of 4, and then I'm going to do n times the accumulator. And then when I get here in the second iteration, it's going to be 4. It's going to be 4 times 5. Oh, it's because I should not return 1. I should return the accumulator. Cool. Cool. Now it works. Live debugging. Cool. So what's happening here is, so first I'm calling this with 5, right? And then the accumulator is 1. So I'm doing 5 times 1, right? So in the next, and the accumulator is going to be 5 for the next iteration. Change for 5. And then in here, I'm going to do 4 times 5. As you can see, I'm doing the exact same thing as before, but I don't need to have that n right here, which is what was preventing me of being able to not stack all those frames. So if I run this like this, you can see I still have all the frames right here. And that's because on the latest version of Node, they don't have, they don't allow you to use the flags that allow you to perform tail call optimizations. So I'm using right here Node version, nvm use 7.10, which is the version that has the flag which allows you to do tail optimization. So in order for you to do that, you gotta be in strict mode. So you save that. So if I run that without the flag, as you can see, I'll be stacking calls. As you can see here, I'm stacking lots of calls. But if I use the harmony tail calls flag, oh, that's not the file I want to run. It's Factorial Live. As you can see, I only have one single frame on top of the stack for every call, right? Because on every call, I have all the data I need, so I can just pop up the other frame, right? Can you see the difference? Node Factorial Live, lots of calls. When I use the harmony tail calls flag so that I can have tail call optimization, proper tail calls actually, bam, only one frame in the stack, right? Cool. And actually this is different from tail call optimization, and it's very important to highlight this. There's like a huge issue on GitHub on the proposal for proper tail calls, where people discuss the real meaning of tail call optimization and proper tail calls and all this stuff. So it's really interesting to read that discussion. If you're into recursion, just Google for the TC39 repos and then go for the repo with the proper tail calls proposal, and you can see all of this there. And this is actually something that should have been implemented with ES6. It should have been shipped on all browsers. I think only Safari supports it right now. Node used to support it behind flags, but now they don't even do that anymore. So we still gotta see what's gonna happen with this. I think it's gonna be dropped. The guys in Safari are really pushing it forward, as far as I know. Yeah, we gotta see what's gonna happen with this. So remember that proper tail calls are different from tail call optimization. So proper tail calls is doing what we've just done, right? Not stacking frames necessarily. And tail call optimization is actually optimizing your code so that it runs faster, because proper tail calls don't necessarily run faster, right? So in here, you got a recursive function. So basically what tail call optimization does is this, right? It eliminates your recursion in order to optimize it. Some people also call this tail call elimination, which is kind of a fun name, because in order to optimize recursive functions, you gotta remove recursion. Isn't it amazing? But proper tail calls can't be that perfect, right? Well, that's because you can have also ghost stacks, because you're not stacking frames anymore, so it gets hard to debug, right? But there's a solution for it. This is a repo for the proposal for syntactic tail calls. And it basically allows you to define when you want proper tail calls to happen or not. So this would allow you to not have them on development environments, so that you can see the stack traces and debug things properly. But that has not gone forward too much recently. So if you're interested into that, I recommend you to read the issues and talk to the guys that are actually implementing it and working on it. But that's the proposal for syntactic tail calls. Also out in the wild, where can you find proper tail calls? So in this issue on GitHub, well, I hope it works. Cool. So some people have done some measurement on how much developers actually use proper tail calls, and they've got some pretty interesting data. So basically, on google.com, for example, they instrumented the code and they found out that only 0.24% of all the functions there were compiled as proper tail calls, and the actual number of function calls that were proper tail calls was 4.14%. And as you can see, even though you've got small numbers here, the numbers here grow quite a lot, and that's because, of course, they're recursive functions. But they've got some notes in here saying that it wouldn't be that much of an improvement. But, well, anyway, it's very interesting data. Lots of you have very interesting comments about it. So, yeah, if you're into recursion, highly recommend you to read that as well. And now, trampolines. So, what are trampolines? Well, trampolines are another way of kind of doing like proper tail calls without Node supporting it, right? So basically, Trampolines, they return functions instead of results. It's basically doing lazy evaluation, right? So we're basically wrapping the function that gets the result into a thunk, and then we only invoke it when we get a function back, right? So this is tail call. This is tail calls happening without proper tail calls. So basically, we're stacking frames as we were doing before, right? And then we unwind. So tail calls, when we do them with trampolines, basically what we call factorial of 3, and we pass 1 as the accumulator. This executes with returns a created value, a created function, which is going to execute with the next values. So basically, instead of returning, instead of just like eager evaluating, we kind of like wrap it in a function, and we only invoke it if the result is a function. Because if the result is the indivisible result, like the last number, which is 1, and then I can just return it, right? So now we can clear the stack because the function has executed to completion, right? Because as you can see, I skipped a few slides here. So so we can just call the function that we returned until we get back the result, right? Well, this is going to be easier to explain once I implement it. So basically, I'm going to remove this because I don't need it anymore. And well, I'm going to use here a function which is suitable for proper tail calls because I need to have all the data inside every frame. So basically, what we're doing is creating a function which trampolines under a function, right? So basically, it takes a function and it gets its result. So fn dot apply. It will return another function because it will be the trampoline function. So it takes a few args. Let's put it like this. So you get an array. Now I'm going to return this function, and we're going to apply those arguments to our function. Does apply need something to use as this? I don't quite remember the signature for the apply function.
Yeah, it does.
Okay, so I'm just going to pass no. Cool. So we're going to call result, and if result is an instance of a function, I will return result. Otherwise, I will return. Oh no, I gotta assign it to result. I'm gonna do while here, and then I'm gonna assign this to this, and then I can just return result. Once result is not a function anymore. Oops, this is not return, right? This is return result. Cool, so now I can trampoline the factorial function and call it with 5, and let's see if it's gonna work. Nope, not harmony tail calls. Cool, it works, right? So as you can see, every time I'm calling factorial, instead of just eagerly evaluating this part, I'm getting it back, and I'm only invoking it if it's an instance of a function. So I just keep calling it while I'm returning a function, right? In order to make this clear, I'm going to add console.trace here again. Oops, I'm doing something wrong, right? Well, sorry, I'm just going to skip to the next example because I've got no time to make this work. Cool. So after all this fail, I'm going to try to derive the Y Combinator, which is a lot harder than this, but probably I'll get this right. And basically, what is the Y Combinator? Well, it's not the startup accelerator. Well, it's this one. It's this thing, right? It's a combinator that allows you to do recursion in a language that does not have any recursion mechanisms. Basically, we'll have no state, no names, only lambdas, right? So get ready for, I want this GIF to play, #science. Cool, so let's get to it. I'll need a volunteer, by the way. Someone who has a calculator on his hands or her hands or whatever. Anyone? Just need a calculator. It's not going to be hard, I promise you. Okay, cool. Okay. So, well, while I'm doing this, you have the very hard task of just keep pressing cosine on your calculator for 0 with the results on radians, right? Just keep pressing it. Just keep pressing it.
Does it even have cosine?
Cool, and make sure the results in radians, right?
You might want to get someone who's competent with a calculator.
Sorry?
There we go. That's
Okay, cool.
You want just cosine.
Yeah, just keep pressing that key while I'm doing my example. If that doesn't bother you that much. Okay, I promise this is going to be useful. So let's create a file called y.js, right? So let's define again our factorial function, right? So we have a factorial function here, which takes a number. Then if this number is 0, we return 1. Otherwise, we do factorial n minus 1, and we do that times n. And let's make sure it works, because you never know. So factorial of 5. Okay, node y.js. Cool. Right. So we've got 120. That's our factorial function. Everything's fine. But well, we want to do unnecessary hard things to make it fun, right? That's what we do in our life as software engineers, right? Make hard things to make things more fun. So how are we going to eliminate this call to factorial here, right? Because I don't want to have any variables that are not bound to the arguments of functions, right? I don't want to have any names here defined outside of these functions. What's the easiest way to remove factorial, this external name right here? Anyone?
Pass it as an argument.
Exactly. So you just pass it as an argument. So this is not the factorial function anymore. So I'm just going to call it factorial generator. Because once you pass a function in, you get the factorial function back, right? So let's try doing the factorial of 0. I'm going to put this in another variable to make it easier to see. So I'm going to do const result equals this. Cool. I'm going to have to pass a function to it, right? Before calling it with 0, because now it takes a function argument. So I'm just going to pass literally any function to it. So this function just returns a string. That's it, all it does. So I'm going to pass literally any function inside of here. And I'm going to call it with 0. So when I do this, oops. Yep, sorry. Generator. Because I'm calling this second one, right? This one. I'm going to comment this one to make sure I won't call it again. Cool. So we got, I'm returning 0. I'm returning n. Oh, brilliant. Such a good engineer. Okay, cool. I'm getting 1 back, right? Well, what happens if I try to call it with 1? Well, I get not a number. And that's because, so the first time I call factorial generator, I pass it literally in function, and n will be 1, right? So n will not be equal 0, and this means I have to call this function, which is literally any function, and that's going to return a string. Doesn't matter what I pass to it. So I multiply a string by n, and this makes it fail. Right? Everyone got it? I'm going to make it more obvious by just returning this, and I'll do console log I was called. So I'll be able to see when this gets called, right? So as you can see, it was called, so we get a string back, and we try to multiply it by a number, and it failed. So how do we make it work? Well, we're going to make it work by passing factorial generator again to it. And now we can calculate the factorial of 1. But what if we try to calculate the factorial of 2? Well, we'll get not a number back. Because the first time we called it, this function was factorial generator. But the second time it was called again, it was literally any function. So we're going to try to multiply literally any function by the number we've got here. So in order to make it work for 2, we just gotta do the same thing we've done before. We can do this, right? Did I miss a parenthesis? Yes, I did. So now it works for 2. And I can make it work for 3. Can you guess how? Exactly, I'm just gonna copy this and put it here again, right? So I can just like keep doing this, and it will work depending on how many nested calls I have. So I can just keep nesting calls, right, until it gets big enough. Can I? No, I can't, right? Well, look, I can even save this as .lisp. I guess it's got so many parentheses, it's valid syntax. So this works until 6, I think. Yep, it does. Cool, so we cannot do this, right? This is not doable. So what we need to do is to make sure the function we will get here is always gonna have factorial generator inside of it, so that we can keep calling factorial generator. Like as long as we have iterations left, we can just keep calling factorial generator, right? So now I gotta introduce the concept of a fixed point. So the Y combinator is also known as the fixed point combinator, and that's for a very special reason. So now that Gideon has been pressing cosine for very long, let's just do some calculations. So Gideon, what's the value you've got there?
The whole value.
Yep.
0.73908.
Cosine. I cannot press it. Let's just do cos of
0.7390
85 13 32 15 161, like this. I don't think that's it. Did I get it right? So this takes quite a while, but once we press the cosine key times enough, I'm going to show you something really cool. Now that Google opened, I'm just going to keep pressing it. Okay, so this is the number we've got back. So basically, when I invoke the cosine function with this number, is it the same one? I think I typed wrong then. Let's see. Okay. So basically, when I call the cosine function with this number, it just returns the same number, as you can see, right? So this is the fixed point of a function. So basically, when you call a function with its fixed point, you get back fixed point, right? This is the fixed point of a function. And this is exactly what we want here, right? Because, well, if you see that fixed point is equal to the result of a fixed point, we can just like keep doing this, right? You can just keep replacing it. And look, it does look similar, doesn't it? It's the exact same thing we've done here. So what we want is to find a way of always getting the function which keeps result which always has factorial generator inside of it, right? We want the fixed point of that. Cool. So let's do that. So what's the most obvious way of always getting factorial generator back? Anyone? Any ideas? Nope? Okay, so I can just call factorial generator with itself, and then I can do factorial. I can define factorial as factorial generator invoked with factorial generator, right? Because then I'll always get factorial generator back here, and then I'll only invoke it when I need it, right? When I get to this part of the function. Otherwise, I'll just return 1. Cool, so I can just do the factorial of 5. And it works, right? So can you understand what's happening here? Okay, so I'm just going to explain it one more time to make sure everyone got it. So basically, when I invoke factorial generator with factorial generator, I'll get what's inside here, right? So if n is not equal to 0, I'll invoke factorial generator with factorial generator itself, getting back the exact same function. So I can just keep calling it, right? As many times as I need, because once it reaches 0, I'll just get back 1, right? That's all we've done. So how do we eliminate, let's call this factorial recursive. Fac rec. I'm just gonna replace it here with same thing. Cool. So how do we eliminate this? Well, we can do this, which is just invoking, which is making it take another argument, which is self. And then we can just do this. And when we call it with itself, we're going to evaluate self, right? So we're calling it with itself here, so that we don't need to call it with itself here, right? Basically, we're doing this the first time we pass a function in. And then f will become the value of self. That's the same thing as this, the exact same thing, right? I'm just evaluating it as soon as I get the first function. But there's a problem there, as you see. Oh, am I doing it right? Oh, I call this factorial generator. I should call it facrec. Cool. Because self here is being eagerly evaluated, so I'm just doing facrec infinitely, right? That's why I'm getting the maximum call stack size exceeded. And how do you delay the execution of a function? Any ideas? Redux, does that remember you of anything?
Rapid, I think.
Exactly. So you just do this. And now you're taking in a number, like x, and you're passing that to self, right? So you only evaluate this once you have x, right? So now we can do this, and bam, it works. And actually, I could even say that this was a combinator if I just called it with itself like this. And then I wouldn't need to do facrec here anymore. But that's not what I want to do, right? That's too ugly. We don't want to do ugly things. What we want to do is get a function which gets the fixed point of our old factorial generator function, right? So I'll write back factorial generator here, just so that we have it around, right? So this is factorial generator. Cool. So how would we do it? Ideas? Anyone? Cool. So does this remember you of anything? This part right here. What's this? This is factorial generator, right? It's the exact same thing. So this is exactly what we're passing in. So we can just make it an argument. Call it f, right? Because we can just pass factorial generator here. And then we invoke factorial generator with itself, and we're going to pass x to it, right? Let's see if this works. No, am I calling it right? F self f x self of xx. What am I doing wrong? Call it here, facrec with the factorial generator. Let's get back here. Cool. So I can pass self, and I can just remove this and make it f, right? Because it's a function. I gotta think this is not easy, right? So once I get self, I'm gonna invoke self with itself. Oh, and I'm gonna do f this. I think that's it. Right, I think that's it. Nope. Well, what was it doing? Gotta think a bit, right? Give me some time. I promise I'm gonna do this. I've got a Swift version that works too, just in case. Cool, so I need to replace this with factorial generator. We know that, right? That's obvious. So you can just put f here. And why can't we pass f here? So we've got self, we're invoking this with itself. Once we've done facrec with facrec, it's going to work. Cool, it works. So basically, what I want to get rid first is this thing, right? With its facrec. So instead of doing this, I can just do this, because I'm going to invoke this function with itself as soon as I define it. So I don't need to call facrec anymore, and I can just call it factorial, right? Let's remove this. It's annoying me. So I can just call this factorial. Cool. So console log unexpected identifier. I missed parentheses. Yeah, I missed parentheses. Cool. I missed another parenthesis there. Here. Cool, now it works, right? We're on the right track. We got back on track eventually. So now we can replace this. Okay, now it's fine to replace this with f, right? And now we can just make f an argument, right? So it takes f, and then we can do factorial of factorial generator. Did I put this in the right place? Let me just check something. I put it in the wrong place. I need to pass in self first, because that's GG, so self is the self function, so this should actually go here. Or not. Or I may have made mistakes again, and I'm just very embarrassed. So this is factorial of factorial generator. This is self. Sorry. That's because I need to pass the function first, right? For it to execute. Cool. I've solved it alone this time. I mean, myself without looking at the answer. And look, we don't even have any external identifiers here anymore, right? So we can just make this pretty and remove self. So let's just replace self with, I don't know, like thanks or G. And then I can do this. And I don't even need this parenthesis enough anymore. So this, after a very hard work, is the Y Combinator. So basically it will find the fixed point for the factorial generator function, and it works, finally. And the cool thing is that it doesn't only work for factorial functions, it also works for any other recursive function with a single argument. So let's implement Fibonacci. So Fibonacci takes a number, and if n is smaller or equal to 1, we can just return 1. Otherwise, we do Fibonacci of n minus 1 plus Fibonacci of, and I like overtime, or is it okay?
Yeah, let's finish.
Okay, cool. This is the last example, I promise you. So once we do this, let's check if Fibonacci works, because we've done way too many mistakes today. Okay, so let's do this. Just gonna, way too many Fibonaccis. Okay, I think this is enough. 1, 2, 3, 4. Cool. Cool, so it works. How do we make this a function which doesn't have any names on it? We wrap it into a function, so we can just do f, and then we replace Fibonacci with f, and same thing here. And now, if we define Fibonacci using the Y Combinator here, let's use Y. Oops, Y. And now we can call Fibonacci, and it works, right? So we can basically do this for any functions with one argument. Well, that's basically it. That's why it's called Y Combinator, because it just finds the fixed point of accelerating startups and just plugs in money, and it just runs that recursively until the money ends. Spoiler, it never ends. Well, that's it. Thank you very much. I'm very sorry for all my mistakes. I hope you have enjoyed it. Once again, I have stickers, and if you want to know more about me or Converge, just come and talk to us. Thank you very much.